Okay, this is the boiler water chemistry of our 3-drum. This was an Erie City type boiler, spreader, stoker, dump grate, put about 90,000 pounds an hour. The feed water was softened water coming in, used sodium sulfite for oxygen scavenger, and also a polymer to keep any suspended solids in solution so you could blow them down. Oxygen control, your first line of defense is your deaerator. Deaeration is huge in any kind of power plant. Get all the oxygen you can out of the water. The chemical oxygen scavengers use sodium sulfite. It reacts with oxygen to form sodium sulfate. There's also DEHA, DHA, diethylamine, hydroxylamine. Kind of a bigger chemical, absorbs oxygen, breaks down, forms acetic acid, which combines with the sodium hydroxide to form sodium acetate. This has some other properties too. It also passivates metals, and it does quite a bit more in the boiler than just remove oxygen. Then there's the good old hydrazine. Everybody probably dealt with hydrazine. It's 35% hydrazine. 100% hydrazine is used for rocket fuel. It is probably considered carcinogen. You definitely want to wear PPE with this and be very careful with hydrazine. But it works very well in boilers. Basically breaks down to nitrogen and water. So 1 part per million hydrazine reacts with 1 part per million of oxygen. Also will form ammonia in this breakdown process and carry through the steam. As you're dealing with softened water, we have calcium and magnesium bicarbonates that are converted to sodium bicarbonate in the softener. So we have our sodium bicarbonate coming in the feed water. Bicarbonate, with the heat, it breaks down to sodium carbonate. It releases carbon dioxide. And then your sodium carbonate, it breaks down again to sodium hydroxide. Also gives you CO2. It's the CO2 and the O2 leaving with the steam. That'll cause condensate corrosion. When the steam condenses, you have your water plus carbon dioxide. It forms carbonic acid. This will react with the iron in the condensate system to form ferrous bicarbonate. You'll see this type of corrosion in steam lines. The bottom of the lines will thin. You won't see the pitting, but you'll see a thinning of the metal. This is your CO2 corrosion. Real common where the steam starts condensing. The ways to protect your condensate system, you can use a neutralizing amine. They vaporize in the steam system. They're carried with the steam. Then they drop out when the steam forms water and neutralizes basically the carbonic acid. There's also a filming amine. They're kind of a thicker material. You feed into the steam lines. They volatilize. Then they form a molecular layer on inside of the pipes. It's a polar compound, so form a very thin layer on the inside of all your condensate lines, which keeps the water and the carbonic acid from attacking the lines. One of the big things on boilers, anything that's vaporizing water, cooling towers, any kind of evaporation equipment, you have cycles of concentration. You have your boiler water, total dissolved solids, divided by your feed water, total dissolved solids. This, you can use this to see how much concentration of minerals are in the boiler water. So in this case, we have 3,500 micromoles conductivity, and the feed water coming in is 2,500 micromoles. We have 14 cycles of concentration. So anything in the feed water will be 14 times stronger in your boiler water. Too much blowdown, you're wasting heat and water. All this water has to be heated, and you're blowing it down. Plus you had to treat the water to get for boiler water, so that costs money. Use your blowdowns pretty close to the surface. This is where your layers of higher concentration of impurities will be. If you blow down too much, you're wasting energy. If you don't blow down enough, this type of system will have an increase in pH and a high level of total dissolved solids. Your blowdown reduces total dissolved solids, your pH, and impurities. Since you're forming sodium hydroxide with the breakdown of the carbonates, you can get caustic embrittlement if the pH gets too high in the metal. So as one prompt is, you don't want the pH too high. pH could run like 11 very easily because you're producing sodium hydroxide with the breakdown of the sodium bicarbonate. So you don't have to do anything to bring the pH up on these kind of boilers. You have to blow down to hold it down. One thing you don't want is any oil coming back with the condensate. And any condensate returning, you have to make sure that it's pretty clean. This type boiler is used for mostly process steam and heating steam. It was shipped a long ways, so we didn't get much condensate back. So there's a lot of blowdown. But for boiler efficiency, cycles of concentration, boiler blowdown is really critical. This example used total dissolved solids. This is a pretty accurate way of doing it. If you're using steam flow meters and feed water flow meters, they're hard to get really accurate. But you can also use feed water flows. There's several different ways you can do this. The bottom line is you don't want to blow down any more than you have to because you're wasting water and chemicals. So in this example, about 14 cycles of concentration is about where this would run if you're trying to hold 3,500 micromos conductivity. If this gets too high, this will start foaming and priming. You'll get little steam bubbles. They won't break. Pretty soon this thing starts filling with foam. Then it'll start carrying over and plugging up your superheater. You need the dissolved solids will drop out in your superheater and plug that up. So it's real critical to maintain your parameters of your boiler water chemistry.